So next up is a talk about Fiano, which is a great tool to inspect UEFI binaries. And yeah, that's all I'm going to say about that. So thank you, folks. And please have a round of applause for Ganshun Lim and Ryan O'Leary.
So hi all, I'm Gan, and that's Ryan. And we both work at Google. And today we're talking about Fiano. And so before I start about Fiano, I'm going to talk a little bit about why we did this project. And the reason, before that we first thank Ron, Julian, who is not here, Andrea, who is I think was not here, and Nikolai and Teddy Reed for their code and contributions. Right. Now, the reason we started Fiano was for Linux boot. Right? And for those of you who are still not familiar with Linux boot, basically we stuff Linux inside the UEFI firmware image. We take advantage of Linux drivers, and we take advantage of process isolation. Right? So disk boot and net boot are all in their separate processors, can't corrupt the memory from one process to the next one, or it's not easy to at least. And all these functionalities are performed by Linux. Right? For more information, visit linuxboot.org. Now, the problem. So the problem is that vendors kind of provide binary blobs without source. Most commercial off-the-shelf systems you get today, the firmware is just on the SPI flash, and you don't have source to it. You can't edit it. You don't know what's on it. All right? And sometimes you want to analyze or modify these images. UEFI itself was designed to be modular. Right? There's a whole bunch of different DXEs or PIs, and it was built in a way that you ideally should be able to swap pieces out at will. And so there are a lot of applications for Fiano. The first, which is why we did it, is so that we can insert a Linux kernel in there. Right now, the whole image is just one giant binary. And without something to make sense of what goes where and how do we insert Linux boot in there, we can't do that. The next is we can remove DXEs that we don't need. Especially like once you have Linux in there, we don't need the AHCI driver, we don't need the IP stack, we don't need the TCP stack, we don't need DHCP, a whole bunch of stuff, right? Sometimes you want to do security forensics. There is a startup that's actually already using Fiano to extract the entire UEFI binary and split them up into its constituent individual DXEs or PEIs, and then run malware analysis on it. They're collecting firmware images from people who submit them online, and they're just running these kinds of tools to analyze all of this firmware. And sometimes you just want to quickly prototype something, right? I don't know if how many of you have built UEFI images. The build tends to be long. It depends on how complex it is. Sometimes you just want to change the binary. Let's say you want to change the shell prompt or something, right? And this is not strictly specific to Linux boot. It can be a DXE. Right? You just want to change a print. You can compile that separately and then use this tool to insert it and replace those binaries rather than recompile the entire image. So the first thing was the way we used it, UTK, which is the tool. Fiano is the library. We use it as a build tool for Linux boot. So we take the existing ROM image, read it out with flash ROM, and whatever else is on there. And we add Linux EFI into it using UTK. In this case, we replace the shell, because the shell is usually not load-bearing. The shell is just a nice diagnostic debug tool. So we replace that safely because we know it's unlikely for that to be important, and we have the Linux boot firmware image. In the case for firmware analysis, we can again read out the entire image, and we say extract it to this folder. And this goes through the entire image and dumps every single binary in there into this folder with a JSON file at the top to tell you what the whole structure is. So for those of you who are not familiar, I'm going to go through a bit about the anatomy of a UEFI image. And the blue parts are Intel specific, but the general structure is the same. So first you have the entire image. On Intel platforms, you'll have the IFD, the Intel Firmware Descriptor. And Intel does separate their image into a couple of sections, a couple of regions. The ME region, the Gigabit Ethernet region, the BIOS region. And for the most part, we only concern ourselves with the BIOS region. We don't have parsing for the ME region or the Gigabit Ethernet region. We just focus on the BIOS region. In the case of like AMD ROM images or QEMU, OVMF ROM images, or even ARM UEFI images, usually you don't have the descriptor, you don't have the regions, you start right at the next level, which is the firmware volumes. So in the image, you have a whole bunch of firmware volumes, and in those firmware volumes, you have files. Right? Inside each file, you have sections. And it would be this simple, except for the fact that now in sections, you can have more firmware volumes, and you can have more files and more sections. And this leads to sometimes very complicated nesting behavior. And usually we see that for compression purposes. Right? So what else can UTK do? We can list the entire set of files in the image. We can extract all of them, as I said. We can replace components in the image. We can dump specific files, and we can validate images, and more. So how do you use it? Right. So this is the first example. I want to see what's in the image. I say UTK, I pass it the ROM image. I type table, and I pipe the output to less. And here you can see this is a QEMU OVMF image, and you can see the different firmware volumes and the nesting. You can see, oddly enough, this starts with PEI at the beginning of the image. Usually PEI is at the back. And you can see the different types of sections. You can see the compression section, the volume image section, which is the nested volume. And you can see the different sizes in hex on the side. This is the first way and the first command we usually do to kind of get a sense of what does this image look like, what's in it. Now let's take a little bit of a closer look. So we can say UTK image, find me something that starts or that has shell in it. Right? It takes a regex, and it dumps JSON about the whole struct in question. What's the GUID? What's the size? What does it look like in general? Does it have a name? Does it have a UI section? We can also pass it a GUID instead, if you're familiar with GUIDs. In the case, sometimes UEFI Dixie drivers don't have labels. They don't have names. So sometimes they just have a GUID. So you can use the GUID to find the same thing. If you want to look at the actual binary, you can say UTK ROM image, dump the shell. Right? Dump takes the same arguments as find. You can use this to actually get individual DXEs. You can also use count. Count tells you, oh, there are this many types of drivers, Dixie drivers. There are this many of PI modules, there are this many applications. It gives you a very rough summary of what's in the image. But enough poking around, you want to actually change things. So we can say UTK ROM image, remove the shell, or remove everything that has the word shell in it, and we save it to a new image. Remove takes the same arguments as find, again. Same style, you can pass it a GUID, you can pass it a regex. But the most important thing that we've used so far is the replace P32. So for those of you who are not familiar, all the UEFI binaries at the end of the day look like a P32 executable. Right? So you can compile the Linux kernel with a P32 header on it that looks like makes it look like a P32 executable. And we say, go find the shell Dixie, and we swap out the binary for the Linux kernel. So by the time UEFI starts to run the shell, what it thinks is the shell, it ends up starting the Linux kernel. And here's where things start getting a little bit more complicated. We can actually chain commands together. So in this case, what happens if you want to remove all of the IP stack, all of the DHCPs, TCP, and all that, and add in Linux boot. Right? So here you can chain the commands together. We can say UTK ROM image, we remove all of them, remove something, replace P32, and then we save at the end of the day. So you can put all this together and put them in your script, right? And we can chain more and more things together for complex operations. At the end of the day, you could even output a table to see what's in the new image that you've just modified. Next, I'll hand to Ryan, who's going to talk to you a little bit more about another problem with modifying UEFI binaries.
All right, thank you, Gon. So a big challenge we had in Linux boot is we had to make room inside of the firmware volumes in UEFI to put Linux. Oftentimes, there's not enough room. For Linux, you usually need like 2 to 3 or maybe sometimes even 4 megabytes. And to get that room, you have to delete drivers from the firmware volume. So there's also other reasons you would want to remove drivers. They could make your boot time faster. They could remove attack surfaces or simplify your firmware. But the big question is, how do you figure out which drivers are safe to remove. So each Dixie has a dependency section where it states which protocols they depend on, so which GUIDs they depend on. So looking at this problem, you might think you can make a dependency graph of all the Dixies, easily figure out which ones you don't need, delete them, and that's that. But there's a fundamental problem here, is that there's a difference between file GUIDs, the GUIDs used to define a Dixie, and protocol GUIDs. So when a Dixie loads, it registers protocols, and each protocol has a GUID, and the dependencies are on the protocols. So you can't statically, without running the Dixie, you don't know what protocols it registers. So you can't make that dependency graph with a tool like Fiano. You have to actually run the firmware. In addition to that, oftentimes the dependency section of the Dixie isn't accurate. It might be missing dependency. So we made this tool called Dixie Cleaner, which what it does, it combines Fiano, the static analysis of Fiano, and also running the firmware on a machine. So essentially what you do is you remove a single Dixie, try booting it on the machine. If it boots up properly, you run some tests. If those tests pass, you consider that Dixie not to be load-bearing, and you can delete it. If those tests don't pass, that Dixie is considered load-bearing, and you keep it. And you repeat this for each Dixie. And once you've done it for each Dixie, you might have deleted a Dixie that another Dixie depends on, so you do it again. And this algorithm is essentially n squared, but usually on the first pass, it deletes like half the Dixies, and finally you don't have to do more than one pass. So I'll give you a demo of running this tool in QEMU. On actual hardware, it's a lot slower because
you have to wait for the boot cycle. Basically.
Yeah. So this is it. So essentially, you pair Fiano with a script, and the script, Fiano itself doesn't know how to flash the firmware onto your machine and boot it and test it. So you write a script which performs the flashing, performs the booting. In this demo, the script essentially runs in QEMU and checks to see if a kernel booted. And you see when you run UTK on the image, it begins with the first round, then it tries to remove one Dixie. It's a bit small, but it tries to remove a GUID. And then it says successfully booted in QEMU. And it knows you could delete that GUID. Then it tries the next one, and it was successful. So you could delete that one too. Then it tries the next one, and it says failed to boot in QEMU, which means that is a load-bearing Dixie, and you have to keep it in there, at least for this pass. And it keeps doing that for all the Dixies in the firmware volume. So we ran this on, hold on. I need to work up to the slide. So we actually ran this on a tie-in board, and we found that that board had 424 Dixies to begin with. And after we ran one pass of this tool, we ended up with 214 Dixies, which is about a 50% removal. And the boot time became much faster. And doing this test, I believe it was about 4 days, so like over a weekend or something. So it's actually, during this conference, how many of you are from Germany? I was talking with a few of you, and you mentioned that in Germany, Dixie means something else. It means it's a word for a portable washroom. And I found that quite fitting. Cleaning Dixies and the dependencies between them and which ones you don't actually need. So Fiano is actually a set of multiple tools. So UTK is one of them. There's a few other tools in this collection. So there's GUID to English. That's Shakespeare here. So GUID to English, what it does is it finds all the GUIDs in a file. So usually it's like a log, and it appends like a textual, like an English representation of that GUID afterwards. And it works on stood in and stood out. So you could pipe your like minicom or whatever program you use to read serial output through GUID to English, and it just puts readable English representations of what the GUIDs mean afterwards, because no one can remember like GUIDs themselves. And the way we found the English representations, we have a big map in our Go code and with about 1,000 GUIDs. And we essentially got these GUIDs from looking at EDK2. We have like a little script which builds out of the build files. It's very convenient. Another tool we're working on is the Linux boot readiness check. So we find a lot of people, they want to put Linux boot on their firmware, but they don't know like how easy it might be, or if they want to change the layout of their firmware to make it easier. So essentially what this tool will do, it has a set of rules, which will, which are rules which, if they were applied, it would make the firmware easier to put Linux boot on. So for example, free space, we prefer that there's more free space available. 8 megabytes might be a bit much, but the more, the merrier. The compression method, so UTK right now mainly works with LZMA or standard compression methods. There's some esoteric compression methods, which some firmware volumes use, and there's not really any reason not to use LZMA. It's fairly good. So there's a bunch of rules we have, and this tool will go through the rules, see if the rules apply to your BIOS, see if they pass or not, and it'll give you an explanation of which ones failed and how you could improve your firmware layout and firmware image for them to pass. So in summary, we have an easily scriptable tool for parsing and editing UEFI firmware volumes. It's written in Go, it's unit tested, it's type safe. It helps you develop Linux boot systems. It's fast. You could find the source code online. You could contribute to it. We have tools such as the Dixie Cleaner. We have the GUID to English. We have the Linux readiness check. And what now? So how can you help, or how can you use this project? So everything's on GitHub. It's very easy to get started. You install Go. You run go get to download it. That installs UTK into your path, so you can just run it. If you want to contribute, we have an issue tracker if you want to fix bugs, so we could file new bugs. We're really interested if you run this tool on like new firmware images. We're striving to support as much firmware as possible. And we also have a chapter in the Linux boot book if you want to like read more into detail about Linux boot.
Yeah, especially last bit about the firmware images. We have a very limited set of firmware images we can try on, just because we don't have that many. So if you want to try this on your own image and send us the results, please do. Right? We're very curious every time we run on something else that doesn't work and we fail in some interesting esoteric way. So,
all right, I guess any questions?
Well, that was fast. So please have another round of applause for Ryan and Gun. Yeah, and we'll have a lot of time for questions, so please just line up at the microphones and ask your questions.
So I have 2 questions.
Yeah.
One is that did you only try on the Fiano core, also, or any probability bias like the AMI inside bias?
we have,
Or this tool is able to work?
yes, we have run them on proprietary BIOSes. I mean, that was the original design, and it was useful for us for doing some prototyping on, for example, the OCP Winterfell board. That's how we develop Linux boot there as well.
So currently our CI system only runs it on the EDK2 OVMF BIOS.
Because that's the only one we can actually submit to GitHub.
Yeah. Because other ones are proprietary and
Yeah.
licensing
I
restrictions.
better to test on my BIOS.
Yes.
Okay. So, and how about if there's for the compressed Dixie driver? That's the compressed algorithm matter. Like someone may use the standard lib or there's a LDMA. Will that impact the decompress for your tool to analyze the Dixie driver?
As long as it's been compressed with LZMA, that's our tool is fine. So our tool actually, to decompress and recompress LZMA, our tool has a built-in Go based LZMA decompressor. But by default, it uses whatever's on your system. So whatever your system LZMA or XZ supports, we support that, right?
Yeah.
So then we have noticed that sometimes when you decompress and recompress it, of course the size changes because the compression algorithm or like the options are slightly different. So you will see things shift a little bit or grow in size.
Yeah, that's a big problem too. So this tool, if you extract a firmware volume and recreate it without making any changes, you might expect it to be the same, but it differs because our compression algorithm was different from the one that originally compressed it. So it's not, the tool isn't really, it will always recompress it to the same thing, but it will recompress it reproducibly, like it will always recompress it to a new thing which is the same if you run it multiple times, but it won't be the same as the original one.
Thank you.
Okay, so I've got a question about the process you're using for determining what's load-bearing code and what isn't. It seems like that it's those modules that aren't running or running suboptimally might have another purpose that you couldn't detect just by booting, like they work when a particular piece of hardware is installed, or they're doing something that's kind of security focused, and so pulling that out might have a unintended side effect when you change configurations. Or so how do you have anything in your process where you could add other criteria aside from just booting to determine if that was safely run?
So in the test script, you could put whatever testing you need. So for example, Ron developed this tool called DUT, the device under test tool, and it would check to make sure you could connect the network and that the PCI was working. Other tests you might include is chipsec for security.
That was what I was going to suggest.
But it's really up to the user. So you just pass in whatever script you want to be run post generation of that image.
Okay.
That must include, of course, the whole step of flashing and running and booting that system and then running your test. But it's up to the user to define what they want to run.
Yeah, because load-bearing code depends a lot on your perspective of what you're doing with the system.
Definitely.
Okay, thanks.
Okay.
I know you guys also try to boot Windows. So when you run this tool, later on you try to boot Windows, do you find that you might need some Dixie back?
So I'll leave this for Ophir's talk because where's Ophir? Ophir, are you here? Nope. Oh, there you are. All right. He's going to talk about that tomorrow, or is it, I think either tomorrow or the day after. But as far as tomorrow, okay, yeah. But as far as I know, when we run Windows, we don't actually use any of the existing UEFI Dixie drivers. We implement most of the functionality using Linux, right? Because a lot of it is very simple stuff like read this block device, get me this, give me the memory map. And there's a surprisingly small number of services that are actually requested by Windows, and we implement them all from Linux rather than using the existing ones.
Great talk. Are you envisioning to use this tool on the physical flash that you can actually change modules on the runtime?
That you mean like?
So right now, I assume this you're operating out of offline, right? I mean, you have a UEFI image, and you can open the image, and you can edit that content of the image. I'm asking you, think that you could do even on the physical flash that you could?
Yes, there's no reason, because what will happen is that you ideally use like flash ROM internal, right, or something to read your own flash. You could modify it and then use it to write to your own internal flash. I would not recommend it in case something goes wrong, but there's no reason, because this is a tool to operate on the binary image. So as long as you have a mechanism for reading out the binary image and writing it back, right, that there is no difference from this tool's perspective. Now, when you do internal flashing, and if you get it wrong, then can't help you there. But
the second thought, I mean, I saw that your tool basically removes the dependencies, the unused components from the image, right?
Yeah.
So if you're building that image, why would you even include those?
Sometimes it's because when vendors build that image, it must work for everybody, right? And it kind of has to fulfill it must work for someone who's buying this off the shelf and planning to do whatever they want with it.
Yeah.
If we're doing Linux boot and we plan to insert Linux kernel using Linux drivers, we don't need a lot of that functionality. So to us, we can remove it. Right? And it's not immediately obvious from looking at it which ones are safe to remove. Like IP stack, kind of clear. Some of the other things I didn't know about what's an ISA bus. Right? I didn't know that. So it's not clear. yeah,
Yeah.
which one is important and which one's not.
Thank you.
So as part of your process to determine which Dixie drivers are load bearing, you're editing the binary, you're flashing it back on,
Yep.
and seeing the boots.
Yep.
At this point, I would have thought most systems were NIST 800-147 compliant. So how do you get around that to flash
So say that again. Most systems are what?
the NIST 800-147, which requires the flash images be signed? How are you getting around
So
that?
it won't work with boot guard on. That's one thing. So if you're talking specifically about like something like boot guard, which verifies the signature upon boot, right? Yes, that won't work. Most of the stuff we've done so far up to now has been on hardware that either specifically does not have boot guard turned on, or you would basically need to be able to have sign it. Right?
Okay. Well, I can see how boot guard creates the same kind of challenge. But even before boot guard, there was, for like the last 5-6 years, the NIST 800-147 compliance stuff, which meant the image that gets flashed on the system must be signed and verified before it gets landed. And it sounded like you were doing flashing, landing these images you had modified.
So I'm not sure what
even
actually
without boot guard
enforces
that.
I wasn't familiar with that spec, and I'm not sure what actually enforces that, because most spy flash chips, I think, don't have signature verification built into them. So like, we literally have a clip, and like we clip to the spy part directly.
Well, that's what you're doing?
Yeah.
Okay.
Yeah.
And yeah, that's how you get around it.
Yeah.
You're going straight to hardware.
Yeah.
Okay.
We still have a lot of time for questions. No? Okay, then. Thank you, guys. And please have another round of applause. And